We're continuing with section 15.6, change of variables. This is example number 4, and it's let G be the transformation given by x equal to u squared minus v squared, and y be equal to 2uv, and let S be all points u and v such that u is between 0 and 1 including, and v is between 0 and 1 including. Find the image R equal to G of S, the Jacobian of G, and the area of R. So this is not the way you typically see the transformations. Usually you choose a transformation and you see the pre-image. This time the pre-image is given and you're finding the image. So let's go through this and see how it works. First of all, let's draw region S. Region S is down here in the UV plane, and it's basically a square shape, and between points 0 and 0, 1 and 0, 1 and 1, and 0 and 1. Now, what is the transformation? Transformation is just G of u and v such that the x value of G is this and the y value of G is that. Now let's try to now this G takes every u and v into an x and y. Now let's try to see how each point in the boundary is going to be affected. Each point in the boundary of S, where does it go under G? So we start with and we have to have some plan when we're discussing the boundaries, because there are so many of them. We have to have some plans. So the plan is to start from the lower boundary down here. This is all, first of all, V component of every point on this boundary is 0, and U component is between 0 and 1. So that's the one that we're looking for. And then if I plug in U and 0 into the G, I will get, in here, I get u squared minus 0 and 0. So that's why G of a u and 0 is going to look like that. Now the next part is, what does it mean? Because I still have G of u and v, it still has u in it, but I want it to be a point in the xy plane. This is a parameterized point in the xy plane. So what we do is we eliminate u in there. So what does it mean to have u between 0 and 1, and then the first coordinate u squared, and then the second coordinate 0? That means that we're on the y equal to 0 line, and x is going to be x, which is u squared, is going to run between 0 and 1. So the image is right here. See, y equal to 0 and x is between 0 and 1. Now let's try to pick another boundary. Let's go with this one. And so this boundary is, this is the line segment, x equal to 1, I'm sorry, u equal to 1, and then v runs between 0 and 1. So u equal to 1, V runs between 0 and 1. That's the second one. Plug it into your transformation. Plugging it into your transformation, and then you get g of 1 and v is equal to 1 to power 2 minus v squared and 2v. Okay, so that's this. Again, this is the parameterized form of the point in the xy plane after you plugged it in. So what you need to do is to eliminate v between the two of them. And how do we do it? It's like x is equal to 1 minus v squared and y is equal to 2v, and I'm eliminating, and so I solve for v in here, v equal to y divided by 2. I plug it back into here. I get x is equal to 1 minus y over 2 to power 2, which is 1 minus y squared over 4. And that's the equation of the piece of the line in the xy plane. Notice that v is supposed to run between, v right here is supposed to run between 0 and 1. Therefore, y, which is 2v, has to be able to run between 0 and 2. And so this is the second piece. And you see that there is a continuity between them, however we use that word continuity. Now, let's try to do one more bound. And so let's go over this bound. And so this bound, the purple one, is you can see that over there v is equal to 1, and u runs from 0 to 1, but in the direction that I'm saying is going to be in the opposite direction. So it starts over here, the point over here, u is going to be 1, and then over here u is going to be 0. Now, in either situation, what we want to do, we want to plug that in to our g. So g of u and 1 is going to give me u squared minus 1 and 2u. And so that's this part. And now that we have that, what we want to do is we want to basically eliminate u between x and y. So x is u squared minus 1, y is 2u, and u, we solve for u to get y half, and so x is going to be y half to power 2 minus 1, which is y squared divided by 4 minus 1. Notice that u runs u runs between 0 and 1, so y runs between 0 and 2, and it's again starts from 2, runs to 0. If you graph this one, this parabola, it would look like this. Now the last piece. What is going to happen when we're running the last piece down here? And so the last piece, or the green one, I can see that u is equal to 0 here, and v runs starting at 1 and runs back to 0. And so again, the similar song and dance, I have to basically plug in 0 and v into g over here. And I get minus v squared and 0. And if you look at this, and this is x and this is y, what you get is y equal to 0. But it also gives you a bound for x because v runs between 0 and 1 and between 1 and goes back down to 0. And then negative v squared is going to run between -1 and 0. So this is basically that bound. So we figured out all the bounds, and then it's safe to assume that what is inside here will go inside there. So S, every point in S, when under G, so any U and V in here under G will land in here. That would be the image of S entirely. That is, this entire thing is G of S. So now that we figured out what S is and what R is, we want to figure out one, the Jacobian, and two, the area of R. And so there are multiple ways of finding area of R. We want to find area of R using a transformation. So let's go back to the transformation itself. So now I want to find the Jacobian. Which we denote by the partial U and V. So what does this mean? This means that this part is x. Okay, so this means that we're finding the determinant of partial x with respect to u, partial x with respect to v, partial, this one is y, and I'm gonna go y with respect to u and y with respect to v. And so x with respect to u is 2u, x with respect to v is 2v, and y with respect to u is 2v. See this one? 2v is the constant, and u, and then y with respect to v is 2u. And so it becomes 4u to power 2 minus, oh, I'm sorry, there was a negative sign in here, minus plus 4v squared. 4u squared plus v squared. Which is going to give us 8 third. The last but not least, you could have actually figured out the area of R using your calc, basically one variable calc. And how would that work? You would break down the integral into two regions, and the region 1 would run between 0 and -1 and 0, -1 and 0 of what is basically solve for x, and you get solve for y, and you get x minus 1 times x minus 1, the square root of that, and times 2, and you want the positive side, dx. And then similarly from 0 to 1, integral 0 to 1, solve for y, and you get 1 minus x, square root of that, times 2, and dx. And in other ways of doing that, also you can find the two integrals, one going this direction and the other one going this direction, and all of those are valid numbers. By the way, even these two are symmetric, so you can only you need to only figure out one of them basically. So the other method that we can use to solve this is using the calculus of one variable. And so look at this. This side, this side is in this area and this area are very symmetric, and so I can find the integral over this area. It's solve for x, so I'm gonna do integral 0 to 1 with respect to y, and then 1 minus y squared divided by 4, and I multiply that by 2 because there are two of those, and I find this area. So this method may not, the method for Calc 3 may not be the best, but it gives you good practice for transformations basically. And a lot of times when transformations are most likely used, the computation becomes a lot more complex. Now let's do iClicker question section 15.6c. And so this question is asking the transformation of u and v is negative uv for x and u squared divided by 2 plus vu minus v squared over 2 for y. What is the Jacobian of the transformation g? And I suggest to pause the video and think about it and come back. I hope you paused, and so let's continue. And so what is the Jacobian? And this is the format that we are getting, and literally it gives us the basically it gives us the scaling factor. We make the absolute value of that to make the scaling factor. And so this is the notation again for this. And so the partial of x with respect to u is going to be negative v. The partial of x with respect to v is going to be negative u. The partial of y with respect to u is going to be 2u over divided by 2 is u, plus in here it would be v. Partial of y with respect to v, and this is 0. This one is going to be u, and then this one is going to be minus v. And then when you multiply it through these two together, and you get negative uv plus v squared, and here minus u times that, which is going to be plus u squared plus uv. So uv and uv simplify together, and you end up with u squared plus v squared. And so the answer is B.